All right, so now that we've successfully separated out our data, let's visualize it. And for that, we need some functionality from another module. That module is called matplotlib. Matplotlib has a whole bunch of graphing and plotting functionality, and this is the module that will help us create our charts. So let's import matplotlib into our notebook. Going to the very top, where we've got all our import statements nicely organized, let's add another one. Let's say import matplotlib. Now, the specific plotting functionality that we actually need is only a small part of matplotlib. And this plotting functionality is called pyplot. So if we import matplotlib.pyplot and hit Shift-Enter on our keyboard to execute this cell, then we can start creating our charts. Coming down to the bottom of our notebook, in a new cell, we can now create our first chart. Let's create a scatter plot. So let's get hold of matplotlib.pyplot.scatter, open parentheses, x, comma, y. What this line of code will do is it will create our scatter plot for us. To show our chart in our notebook, we actually have to tell matplotlib to show our plot. And we can do this with matplotlib.pyplot.show, and then parentheses at the end. Let's hit Shift-Enter and see what this looks like. After our cell executes, we should see something like this. Now, I want to do a couple of things. First off, I want to simplify our code. And second, I want to prettify our chart so that it becomes a lot more informative. The problem with the code is that it's a little bit long. If you go online and you take a look at some of the documentation, you rarely see code written like this. What people do is they shorten this bit of the code. So what we can do is we can go to our import statements at the very top, and we can create something called an alias for our pyplot. And we can do this by simply writing as plt. And this as keyword gives our pyplot this short name. So we're importing matplotlib's pyplot as plt. And this means we can come down here, and instead of writing all of this and then scatter, we just write plt.scatter. And here we just write plt.show. And just to prove that this works, I'm going to have to execute this cell first, because I've made some changes here. And then I can come down here and execute this cell. And what we should see is the same result as before. So what can we do to make this chart a lot more informative? Well, we can add a title to it, or we can add labels to the axes to make it a lot more clear what's going on. To do that, we can adopt a very, very similar approach to what we did up here. We had some sort of object, then we put a dot after it, and then we told it to do something. Up here, we were using our data object, but with our chart, we're going to use plt. So to add a title to our chart, we simply write plt.title, and then in the parentheses, we provide the title. So I'm going to call this chart Film Cost versus Global Revenue. And when I hit Shift-Enter to refresh the chart, then the title will appear just above. And similarly, we can add labels to the axes. So with plt.xlabel, we can add production budget in dollars to the x-axis. And with plt.ylabel, we can add worldwide gross to the y-axis. Brilliant. Now, what else can we do? Well, first, let's make our chart larger. So if I come up here and I write plt.figure, I can change the size of our chart. And I can do that by setting the figure's figure size with fig size is equal to, and then parentheses, and I can supply a width and a height here. So I'm going to go with 10 by 6. And if I hit Shift-Enter, then my chart will update and become much larger than before. And at this point, what's becoming very clear is that our y-axis and our x-axis are actually going below 0. So there's some space here to plot anything that is a negative number. But if we look up here, we can actually see that for both our production budgets and our revenue, we don't go anywhere near 0. So what we can do for our chart is we can set a range for what should be displayed on the x-axis and the y-axis. To customize our chart in this way, we would write plt.ylim, and then in the parentheses, we set a minimum and a maximum value. So for our y, I think we can go between 0 and 3 billion, just so that we capture this data point up here in the top right corner. So I'll add plt.ylen, and then in the parentheses 0, 3, and then billion. Billion has 9 zeros, I believe. So 1, 2, 3, 6, 7, 8, 9. Let's hit Shift Enter on the cell and refresh that chart. And let's take a look at our changes. Now that empty space below has disappeared. So let's do the same thing for the x-axis. And actually want to leave that over to you as a challenge. See if you can figure out how to add some code to the cell to set the limit on the x-axis to have a minimum value of 0, but a maximum value of 450 million. That way, when you refresh, you should get rid of this white space here, and we should see our chart much more clearly. I'll give you a few seconds to pause the video before I show you the solution. Ready? Here we go. It's very similar to what we did with our y-axis. In this case, we have to modify one thing in our code. Instead of ylen, we're going to go for xlen. And instead of 3 billion, we're going to go for 450 million, which is 450 followed by 6 zeros. If I hit Shift Enter on my cell, then I should see my chart update like so. But we can actually improve the styling a little bit further. One thing we can do, for example, is we can add transparency to our dots here. So we can go to our scatter plot, and similar to what we did here with setting the figure size for the figure, so the overall size of the chart, we can actually set the transparency for the dots in the scatter plot. And we can do that by putting a comma after the y and setting something called the alpha value. So by setting alpha equal to 0.3 and hitting Shift Enter, then we'll see that our dots have become a lot more transparent. And this will give us a good appreciation for the number of data points that we have in certain areas of the chart. So down here, we have loads and loads of movies and loads of data points. And as we go to the top right, there's fewer and fewer films. So where are we at now? At this point, we've done some excellent work visualizing our data. And this has helped us spot some of the clear outliers in the film world. For example, this film right here has had an enormous production cost and also made a lot of money. This movie is called Avatar, by the way, if you're wondering. And looking at this chart, you can see just how out of the ordinary this film was relative to other movies. But there are also some films that have made very, very little money but cost a fortune. And these films are down here. That said, what's very clear from this chart is that most films are actually smaller productions, less than, say, 1 million. And we can see that from this very dense cloud of data points in the lower left-hand corner. Looking at this chart, we can also start to understand more about the relationship or the potential relationship between movie budgets and movie revenue. Because there indeed seems to be some sort of upward trend that's visible in the chart, and higher budget films do indeed appear to have higher revenue. But how much higher exactly? And how strong is the relationship? To answer these questions, we will need to turn to our linear regression. Our linear regression can help us quantify this relationship. But before we do that in the next lesson, let's save our work. We've written quite a lot of code, and it would be a shame to lose it. And I can tell you one thing, trying Jupyter Online is prone to get you disconnected if you leave it alone for too long. So go to File, and then go to Download as Jupyter Notebook. And this is the .ipynb extension. That way, if you do get disconnected, your work is saved, and you can come back here to upload your Jupyter Notebook if you need to continue where you left off. Alright, so we've plotted our data and we suspected there's a relationship there. Now it's time to talk about the algorithm that we will use to help quantify this relationship between budget and revenue. In this lesson, we're going to talk about the theory behind regression. So we know what our real data will look like, but let's illustrate what the algorithm will do with a stylized example to help build our intuition. Our linear regression will get 2 kinds of data. It will get our film production budgets, and it will get our film revenues. The budgets will be our feature, also called the independent variable, and the revenue are what we are trying to estimate. That will be our target. What the linear regression will do is try and represent the relationship between the budget and the revenue as a straight line. But here's the rub. What kind of line? Let's think back to high school math class and let's think about what describes a line. From our math classes, we know that we can plot y as a function of x, and that's a line. And if we cut the y-axis at 10, then we say that our line has an intercept of 10. And if every time x increased by 2 and it made y increase by 1, then we say that the line has a slope that is equal to 1/2. In that case, our equation would look something like this. Y is equal to 1/2 x plus 10. And that means that the generic equation for our line would be something like this. It would be y is equal to mx plus c, where m is the slope and c is the constant. So let me ask you this. What part of the equation for the line would tell you about how strong the relationship is between x and y? In this case, the slope is the key. The slope tells us how much y will change for a given change in x. The larger the value of the slope, the steeper the line becomes. Let's take a look at an example where there is no relationship between x and y. Let's take a look at an example where there is no relationship between x and y. If there is no relationship, then we would simply have a straight line. In this case, the slope would be equal to 0. But if there is a relationship between the two, then the slope would be quite steep. And the stronger the relationship, the steeper the slope. But here's the thing. There's a big difference between machine learning and pure mathematics. In machine learning, we don't actually know the true relationship. And that's why we refer to the slope and the intercept as parameters. And these parameters have to be estimated for our linear regression. In fact, we even use a different notation. In our notation, we will replace the c for the constant with theta 0. And the slope coefficient will be written as theta 1. And also, we'll change the order in this equation. So we'll have the constant first and then the slope. And instead of writing y, what you'll also often see is h theta x, where h stands for hypothesis. This kind of notation is very popular in machine learning. And even though it can look quite intimidating when you first see it, all you're looking at here is the equation for a simple line. And the reason I'm showing you this right here is because if you ever pick up a book on machine learning or you're reading some articles on the internet, you're going to be confronted with notation that's very, very similar to this. But at this point, we still haven't talked about where the line ultimately comes from. How do we know which line to draw? Looking at the data, we just have data points. There is actually no line, right? And as a matter of fact, you can draw a whole bunch of different lines through the same set of data points. So which line is best? Which line would you choose? Which line has the best possible theta 0 and best possible theta 1? If our data set looked just like this, our job would be easy. All we would have to do is connect all the data points with a straight line. And this also seems like the best option, because we would know that in this case, our estimates for theta 0 and theta 1 would be very accurate. However, real data looks more like this. If we were to draw a line through this data, then there would always be a gap between the actual value and the line. In other words, there would be a difference between the actual data point and the point on the line. The point on the line here, that's called the fitted value or the predicted value. But let's talk more about these gaps, because it's these gaps that will help us choose the best possible intercept and the best possible slope for our line. These white lines are actually called residuals. Now, why will the residuals help us choose the best possible line for our data? Let me show you another line that we can draw to this data. If I draw a line down here, then what we see is that the gaps between the data points and the line are much larger. The residuals are way bigger. So the residuals can tell us something about how good the line is that we're drawing on this chart. So now we have a measure by which to compare the different lines that we can draw through the data. All we have to do is look at the size of the residuals and choose the line with the smallest residuals. And that's great, because now our algorithm has a very clear objective. The goal of our linear regression is going to be to calculate the line that minimizes these residuals. But how exactly should that work? let's take a look at that first residual. That first residual is going to be the difference between the actual value, the y1, and the predicted value, which is the one on the line. And that second residual would also be just the difference between the actual value in white here and the fitted value in green. And the same is true for that third data point. Now suppose we actually have calculated the values for these residuals. And these residuals have the values 10, -6, and 4. In this case, what we can't do is just add them up and find the lowest sum, because that second data point is below the line. We have a negative number here. So what we have to do instead is we have to turn all of these numbers positive. And the way we can do that is by squaring the residuals. Now what we've got is a single number, the sum of the squared residuals. This is the number that the linear regression will try to minimize in order to choose the best parameters for the line. In other words, to find the best possible fit for our regression, what we need to do is we need to choose an intercept, the θ0, and we need to choose the slope, θ1, that minimizes the sum of the squared residuals. And you'll see this number also being referred to as the residual sum of squares, or RSS. So now that we've talked about the theory and built out our intuition behind our regression, let's implement this in Jupyter Notebook. I'll see you in the next lesson.